All right, welcome to the next night of homework. There's three pieces of this homework. This is part one, which is your NIMSY notes. You also have two other parts. It's a 15-question multiple choice section, which you should have gotten from me in class, as well as a one-page front and back vector exercise. You have a problem set page, and it just tells you to do those three things. So hopefully today you'll have a good working definition of vectors and how to use them and how to make them do what we want. So what is a vector, first of all? Why do we care about a vector? Well, the biggest thing about vectors is that a vector has two very important things. And those important things are a magnitude and a direction. A magnitude and a direction. So if you're taking a look at your notes, vectors has both magnitude and direction. What do I mean by that? Well, my example is velocity. If I give you a velocity and I say something like 3 meters per second, that's not a velocity until I give you a direction. I can say north, I can say up, I can say down, I can say a lot of different things, but I have to give you a direction for it to be a velocity. A scalar, on the other hand, simply has magnitude. It has no direction. It's kind of like an absolute value. So you're going to see that. That stands for the absolute value of my vector. It's just my magnitude. It's just the number. It's 3 meters per second. It's not positive. It's not negative. It's not up. It's not down. It's not left. It's not right. I have no idea where it's going. I simply know how fast it's going. And in this case, it's 3 meters per second. You know how much it is. You don't know where it's going. Examples of vectors are velocity, displacement, force, momentum. All of these things are vectors. Things like time, temperature, mass, speed, they are scalars. They don't have a direction. They just have a value. We'll get to many of those definitions throughout the years. Okay? Because vectors have direction, we will like to draw them as arrows. The tip and the tail method. The tip over here is the endpoint. It's where it's going. The tail, of course, is where it begins. Okay? And it shows direction by where it's pointed, and the length of my arrow is related to magnitude. So for instance, if I had something like this and something like that, I might say this is 3 meters per second to the right. This might be something like 9 meters per second to the right. I'm not going to bust out a ruler on you here, but you should have some relativistic ideas here. The longer one should be bigger. The shorter one should be smaller. Okay? Now, the first way I want to teach you to add vectors is by the graphical method, which is called tip to tail. Now, tip to tail is very simple. When you're given two vectors, you simply add them by placing the second vector on the tip of the first. So for instance, if I have two vectors, one 8 kilometers to the east and a second one 6 kilometers to the east, the way to add that is I'd start my first one at 0. I'd go 8 kilometers to the east, and then I'd pick up at the tip of my first one, and I'd start the tail of my second, which is 6 more kilometers to the east, which I hope you recognize is a resultant of 14 kilometers east. Now, what happens if they're in opposite directions? Well, in this case, I have an 8 kilometers to the east, and then I have a 6 kilometers to the west. Okay? Tip to tail, I'm laying them on top of each other so you can see it more easily, which leaves me with the resultant of simply 2 kilometers east, because the arrow's still going to the right. How do I know? I start at the beginning, I go to the end. I start at the beginning, I go all the way to the end. I start at the beginning, go all the way to the end. That's how we do it. Now, how do you find, however, the resultant when you're in more than one dimension? Well, let's start off with a relatively easy case. What happens if I give you an example where I go 10 kilometers east, and then I choose to go 5 kilometers north? So if I go 5 kilometers here, and I go 10 kilometers down here, how do I add these together? Well, I hope you recognize with relative ease that this is a right triangle. Now, how do you know it turns into a right triangle? Again, tip to tail, and then my final resultant vector goes from beginning to end. I have a right triangle. I hope we realize I can use Pythagorean theorem to answer this. So this is meant to be very, very, very simple. Pythagorean theorem gives you the answer. Now, the problem is it gives me the magnitude. It gives me the number. A squared plus b squared gives me c squared. It gives me the length of my vector, but it doesn't tell me the angle. So to find the angle, I'm going to require a little bit of trig. So that is on the next page. So of course, what's my little bit of trig? Sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Some old hippie caught a high tripping on acid. That's my mnemonic. There's another one they give you there. Whichever one helps you remember it, pick it and remember it. So when I come back to my example here, I have 10 kilometers on the x-axis. I have 5 kilometers on the y-axis, and I want to know my angle right here. Now, some of you, why do I care about that angle? That's the angle off the x-axis. That's how we always mark things off in math class. That's where we mark things, off the x-axis. So what is that angle? Well, which two values do I know? I know opposite. I know adjacent. That means I'm tangent. Tangent's opposite over adjacent. That means it's 5 over 10. And then, of course, to get my angle, I've got to do the inverse. Inverse tangent of 0.5 is simply 27 degrees. Okay? Now, how do you name it? The angle is off of east, so it's 27 degrees. Okay? What? It's off of east, so north of east. This is called a bearing. If you're not good at that, we'll get better at it over the year. Try to see if you can do it. It's not too hard. Maybe Google it if you're not sure how to do a bearing. Now, since vectors, the magnitude of a vector is always positive, what a sign is really telling you, a negative, is telling you to go the exact opposite way. So if I tell you that v is 4 kilometers this way, then negative v would be 4 kilometers in the exact opposite direction. So let's do an easy example that doesn't have negatives, and then let's do one that does. So if I asked you to add 1 plus 2 plus 3, it actually doesn't matter which one you start with, but I'm going to go ahead and do it in order. So I start at 1, I draw them in, I then start 2 at the end of 1, go down, and then I start 3 at the end of 2 and go over. And how do I know what my resultant looks like? My resultant is from the very beginning to the very end. Remember, that's what it is. It's straight there as the crow flies, one place to the other. What happens, though, if I ask you to subtract v1? Well, what you can actually think minus as, isn't it the same thing as plus the opposite? Well, if you add plus the opposite, again, using tip to tail, it's very simple. I start with v2, go up to the right, because that's what v2 is. I'm going to add a negative v1, tip to tail, and then, of course, I have my resultant from beginning straight to end. So this is how I use my graphical method. I've learned a little bit about combining using Pythagorean and trig. Okay. I have one other thing I can do. I can add vectors by simply using components. Now, what do I mean by components? When I give you a vector, say something like this example here in your notes, okay? That vector is going at a very odd angle, 30 degrees above north of east, to be exact. So what I can do is, instead of treating this as one big vector, I'm going to treat this as two baby vectors, v sub x and v sub y. Now, when I do that, using a bit of trig, I get here. And this, by the way, should look a heck of a lot like polar coordinates to you. V of x is my overall magnitude times cosine of theta. My v of y is v times sine of theta. So remember, you can break down any vector into its components by simply doing v sine theta or v cosine theta, respectively. Now, once you've broken everything down into x and y pieces, the reason we like to do this is because you can add all the x pieces together, you can add all the y pieces together, and that gives you one giant right triangle that you can then add together. Okay? We'll be practicing this as the couple next days go by, although that is a skill that'll take probably next block to totally figure out. So let's take a look a little bit at number 1 and see if we can figure it out. This will be the only one we do today. After that, I want you working on the other 2 pages of homework. No more of this. We'll do the rest of these notes in class. So a rural mail carrier leaves the post office and drives 22 kilometers in a northerly direction to the next town. So I'm starting at my current town. I go straight north 22 kilometers. Okay. She then drives in a direction 60 degrees south of east. So let's remember what that is. So east is this way. Okay. So I'm going to be 60 degrees south of east. So here we go, 60 degrees south of east, and I only go 47 kilometers. What is her displacement from the post office? So I want to know, what's this value? What is my resultant? Okay. So I hope you realize that some of this stuff is relatively easy. If I look at my first vector, and I break it down, so let's just say vector 1 in the x direction, and vector 1 in the y direction, I hope you recognize that my first one is just north, which is only y. So it's 22 kilometers north. And I have 0 motion in the x direction. I'm not going left, and I'm not going east and west at all. This other one, though, my red vector, is a little bit different. Okay? I'm going to say v2 sub x and v2 sub y is not going to be quite so simple. Okay? I'm going to take my magnitude, 47, and for x, I'm going to do cosine 60. And for y, I'm going to do sine 60. Now, we need to do one last little thing here, though. We need to do one last little thing. And that last little thing is one of these is not like the others. My x direction is to the right, so that's supposed to be positive. But my y direction is down, and so should be a negative number. Okay. Now, once I've done this, how does this help me out? Let me give you a second, calculate this number, and see what it is. So I now have 2 values of x, one that's 0 and one that's not, and I have 2 values of y. So what I want to do then is kind of redraw the graph in this manner, which is this. So I want to draw it here and here. I want to do Pythagorean theorem, okay, for my resultant. And what you have to realize is that the net of my vx's is simply v1x plus v2x. And the net of my vy's are simply v1y plus v2y. Now I have all of my displacement in the x direction, all of my displacement in the y direction. This is my net vx. This is my net vy. And now I can apply Pythagorean theorem to get magnitude, and I can do inverse tangent to get direction. So I'd like you to try that, see if you can figure the rest of this example out on your own using your pieces. But as I said, this is not where your focus is right now. This is an advanced one. Go back to your 15 multiple choice questions. Go back to your 1-page front and back vector addition problems and see if you can do those ones on your own. I'm hoping they're not too bad. Good luck. See you next block. See you on Wednesday.